is Quynh, a student at Fulbright University Vietnam. In this video, I would like to share with you my final project for computer organization course offered in fall 2023 by Dr. Truong. The project is a student card collateral locker for lending blanket. So basically, there will be a blanket in every locker, and if you want to borrow one, you have to leave your student card before you could take out a blanket. And when you want, only when you return the blanket can you take your student card back. Under the scope of this course, we will simulate this kind of finite state machine using CircuitVerse and provide a demo for the product. So in this video, I will walk you through the motivation for this project and show you a demo and then some notes I have during the ideation process. So if you're a Fulbright student, then the name of the project should have rang a bell. Last year, our school initiated several projects for lending stuff to students. For example, the electrical socket extension corner or the blanket corner. Both are welcomed by many students, but they both face problems of items management. The electrical socket extension corner has to close after several months because all the blankets were lost. And the blanket corner, as an organizer of this project, I had a lot of problem with finding all the blankets back before I could. And as for the blanket corner, we also suffer from the same problem, in which we had to spend a lot of time to collect all of the blankets and remind students on our Facebook groups, things like that. So the point is, as an organizer, it's hard to collect all the lent items, and as students, as someone who also uses the service, I also realized that none of us want to steal these things or want to keep them for personal use, but most of the time we're just lazy or we just forgot to return. And that is where I come up with the idea of a receptionist would be cool. But what is even better is a virtual receptionist where no one had to spend a lot of time staying at the reception table. So here's how the idea would work. So it's a locker with two cells in which one cell would lock a card and one cell would lock a blanket. At a usual state, only the blanket is inside the cell and the card cell is unlocked. When a student wants to borrow a blanket, they will reach the system and then insert a card. And then the system will prompt them to type a passcode to secure the card. Then as soon as the passcode is received, their card will be locked and the blanket cell will be released. They could take the blankets out and use for a while, and then only when they return the blanket and type the passcode that they have just that they entered just then, will the system release their ID card. At the same time, as an organizer, I also realized that we needed some kind of master code so that the organizers could release both cells at any time. So that's the idea. How did we actually implement it using finite state machine and logic circuits? Hereby I will show you a product demo that I've done on CircuitVerse.
So as I enter this project, you can see that its current status is the ID locker is unlocked, there's no ID inside, and so is the blanket locker is locked, but there's no blanket in. To set up as a facilitator, I first have to insert a blanket. Now the blanket is in, I will remove the master code. As a user, and I approach the machine and I would like to borrow a blanket, what I would do is First, as it said here, numpad 1 is not available until ID card is inserted. So first let us insert an ID card or a screen card. Now enter the code 365 and hit enter. So now it says your card is secure. You can borrow the blanket for 3 hours. Please see the counter to see how much time is left. To receive your ID back, please ensure that the blanket is placed in the locker and enter the code you have input. Okay, so say I've been using the blanket for I don't know, for quite a while. I feel sleepy now, and then I take a nap, and then I'm done. I want to return the blanket for the next user to use. So what I would do is I come here. Now the blanket locker is unlocked, and okay, I would like to place the blanket back. So it says here blanket is in. What I need to do is enter the code I've just input into numpad 2. So the code I have input is 365. Then I'll hit enter, and it says password correct, blanket well received. Please take out your ID card. Thanks for using our service. Great. So I'll take out my ID card, and voila, the status is set to blankets is available. Please insert your SIM card. So another student can easily come here and insert their ID card to borrow a new blanket. And so that's it.
So that was a quick demo of how the product works on CircuitVerse. I've made a scratch of how, if it is ever implemented, the physical product would look something like this. There's a card for there's a place for the card, number pad 1 and number pad 2, and then the whole locker will store the blanket. How do we actually came up with the whole product? So as part of this course, we learned the procedure to design a final state machine from scratch. The whole process will start with thinking about what kind of functions we would expect the final machine to have. So I know for sure that it will need something to secure the things that students leave at the locker. The way we implement it is we will allow users to set a temporary passcode, ensuring that their belongings is kept safe while they borrow the blanket. Secondly, we know for sure that the organizer would need some kind of full control for both lockers when they would like to control the system to take out the blankets to wash, or sometimes maybe users could have forgotten forgotten their passcode. Also, we need a timer for organizers to know that has any blankets been borrowed for too long, so that they contact the one who borrowed to collect the blanket back. With that in mind, we've identified all the inputs and outputs that would be needed for the product to work. On the left-hand side, you could see the 3 inputs that I have just mentioned, where the password is saved, whether the new input is the correct password, and whether a master code is input. With those ideas in mind, we start to work on the finite state machine diagram, in which we would record all the states and the state transitions needed for the product to function correctly. I would confess that actually it all started with a very simplified machine. During my ideation process, I started with thinking about this product with only 2 states, available and borrow only. But the new information, or thinking about how the user would interact with this product, added up many states for the machine. And it started from 2 states with only 2 transitions to more transitions, and then 3 states, and then 4 states, and eventually come to up to 6 states. And as we've reached to this 6-state machine, I figured out that I could reduce it to 5 states diagram only, which is here. So with the state diagram, designing the machine is much more simple, which is we know all the procedures during the course. We would identify all lines in the truth table and then implement it using sum of products method to find the logic expression and implement it on CircuitVerse. So that is for the locker status. As you can see, we need something to produce the input of CDE where the password is saved, where the password is correct, and where the master code is input. That is where I added a block right next to it, which is a number pad that will store user inputs and then generate outputs for the main machine to know whether it should release any locker. For this number pad, I used a already designed, very well designed number pad, a public project on CircuitVerse, which is here, and then modified it using the conditions, the defined conditions that we've had in mind. Most of the procedures uses a lot of multiplexer, so we need a multiplexer to decide whether inputs are allowed, and then another multiplexer to decide whether it's time for the timer to show on the screen instead of inputs, and something to reset the number pad, check whether an enter button is hit. We would also need a password comparator. Along with that, I've also attached a master code comparator to ensure that there is some sequence that would always allow the organizers to take full control of the system. When all the plans are set, the implementation on CircuitVerse is pretty simple actually. We've pretty much had everything and just need to put everything down and debug. So that's all the designing process. I will share a little bit about the troubles that I had during the time I do this project. One thing that I've learned during this doing things on CircuitVerse is that theory design and actual application might have some disparity, which is I didn't know that CircuitVerse would have some limitation, and also my laptop might have also some limitation in how much simulation it could work that allow it to work smoothly. For this machine, sometimes there will a lagging occur, as you can see here. It would pop to 000 states before moving back to the original one. So when I was doing this, I didn't know that it's an overloaded or a lagging from CircuitVerse, and I thought that it's something from my project. So I keep on trying to find a bug that probably did not exist, and actually redesign the whole system over and over again, changing minor things like moving the clock outside to have a global clock, or moving the clock back in. And then I try to use a different way of writing down these sub-circuits. Also, I try to do some change with the overall wiring many times, but it always works right when I have just wired the new system, and then if I turn it off the next day, it would not work anymore. And it just goes like that several days until I finally figure out that it's not my system, it's CircuitVerse. So it was a painful procedure, especially realizing one very important thing is that there will be some weird states that you never define but still happen due to propagation delay, and it makes the clock behave incorrectly. This propagation delay is a universal problem because I do see many implemented timers on CircuitVerse suffer from the same propagation delay error. It's actually a fun process where I've learned many things. One other thing is regarding the design. I usually had some. Usually, when you look at a design that someone have designed, you would see spots where you would raise questions. Why did they do it so redundant? And as soon as I do this project, I realized that those redundancy could be the remnants of some ideation process. So, say this 6-state machine could be reduced to 5 states. I actually intended to leave it as 6 states like this, but at the last day I decided to remove it to see whether it would affect the lagging bug thing from CircuitVerse that I didn't know that it's a thing from CircuitVerse. So I realized that turns out sometimes you just have to compromise the whole thing, the whole efficiency in order to meet the deadline. Because if I just keep on redesigning this thing over and over, every time I see some error, it would take forever. Instead, at points I have to accept that okay, we will find some way to fix that flaw at that point instead of redesigning the whole states. So that's the end of my final project report. Before we end, I would like to spend some minutes to give credits to this guy who had developed the original version of the number pack. He also had some great other works on his personal page on CircuitVerse, which I believe deserve more likes. I hope that this video has given you some insights in how to build a finite state machine from scratch, and thank you for watching.